Let me take this opportunity to introduce Benjamin to you. I met him first at the Technical University in Darmstadt when I was teaching, and I noticed him rather quickly, and as circumstances had it, then he started his diploma thesis, and very soon afterwards his PhD thesis. His PhD thesis was already at data from the Alice experiment at the LHC. In his diploma thesis, he worked very hard on getting the Alice transition radiation detector ready for data taking. And that is something which I think is very noteworthy. He is equally good in hardware and software as in interpretation and analysis of data. This is something which you don't find often, but even to this date, while he writes many papers, not only Alice papers, but even outside of Alice papers, he is still the technical coordinator now of the Alice TRD, which is a very substantial job. And especially now as we start the data taking period for the run 3, this is something where you have to be on your toes all the time. Luckily, much of that can be done now remotely. Otherwise, it would be, of course, very much more difficult. Now, after his PhD, he joined the University of Frankfurt in the group of Harry Appelshäuser, and continued to work. And I think all those of you who have followed a little bit the field have certainly noticed him, because he wrote a number of substantial publications even outside of the Alice collaboration. But also within Alice, he's very much instrumental in the data analysis for the topic of today, namely the creation of fragile antimatter, but also of multi-strange baryons, Hypertriton properties, and so on. You will see that. Since about a year ago, he is now senior research associate at Frankfurt, and very much in charge of introducing the next generation of physicists into the game. So this is, I think these are his 3 strengths: that he can work well with young people and motivate them. He writes exciting publications, and at the same time, he's not afraid to touch ASICs and things like that for detectors. So I think we're all very excited to hear what he has in terms of the latest information of the creation of fragile antimatter at the LHC. Benjamin.
Thank you, Peter. In fact, I prepared a lot more than I will show, and I think I will skip some of the material. But I usually always introduce this event display, so it's not a simulation, this is real data. And the black highlighted thing here is an anti-alpha we found in the 2011 dataset. So moving ahead, so I split it basically in an introduction, which I keep short because I guess everybody knows that, and then move to 3 chapters. And in the end, if it's too long, I will skip the exotica, because I think this is connected to the other things rather old before I conclude. So the main driver for me is basically to really explore QCD and QCD inspired predictions of particles, like these dibaryon candidates here, or this lambda n-bound state, which was actually seen by the HiFi collaboration at GSI. They are building a new experiment to confirm their measurement because nobody else saw it. We don't see it. We put an upper limit on it. but we want to go down to helium 5, and this is a hard, so we'll not reach that in run 3 and 4. This is what all of my students definitely showed. We only expect one candidate in the whole data set, but this is something for even more future. But by searching for these guys, we actually test model predictions for the production, which are normally connected to thermal and coalescence model, and I will come to that. And by measuring those particles, we hope to understand the production mechanism. And as I always say, the bases are light anti-nuclei. So this is also the core of my talk today. I will mainly focus on that. So this I will keep short. You know, everyone connected, I guess, knows that we have these pancakes because they're Lorentz contracted, they collide, form a quark-gluon plasma, which hadronizes, and at the end, particles end scattering, and we measure them in a detector, which is connected to that picture in a relativistic time space coordinate system. You see here the two beams colliding. There's some thing where a lot of theory is happening at the moment, is pre-equilibrium phase, but then we form that quark-gluon plasma, have a crossover region because it's a crossover phase transition, and then we have these two characteristic temperatures, the chemical freeze-out temperature where actually the yields are fixed, and then the kinetic freeze-out when also the spectra are fixed, which we measure at the end. So these two temperatures will pop up, that's why I explained that all. And then it's worthy to note that it's an old picture, but the lattice QCD results evolve over time. And at the moment, the critical temperature, which is connected to this crossover phase transition, is of the order 156 plus minus 1.5, if you take the most precise number, but it's in the order of 155 MeV, and it's actually for both groups which do these calculations. So the first model I'm testing with the particles we are measuring is the statistical thermal model. Peter knows it much better than me. I'm only new in that field. I started actually something like 2014 to do my own fits. But you see here, basically all particles are rather well described by this model, which only has 3 parameters. The 3 parameters are temperature, volume, and baryochemical potential. And the good thing at the LHC, we can put the baryochemical potential to 0 in most of the fits, because when you fit it, it gets out to be close to 0. It's basically 0 with larger uncertainty than the value 0. And the volume is usually fixed by the pion. So you can say all other particles are predicted by the temperature. So the temperature is the main player at the LHC, and it comes out from this fit around 156 MeV, which is close to the temperature which you get from the QCD, lattice QCD calculations. And this is then connected to the series of papers and calculations Peter did. So you all know that these kind of fits were performed at different energies, and you get this kind of T versus square root of S behavior. So you get something like a limiting temperature, which is of the order of 159 plus minus 2, which is also close to that 156. And you see clearly when you do this fit from the baryochemical potential versus the center of mass energy, you see that it drops to 0. So basically we expect it to be 0 also from these kind of measurements. And the good thing, you can use this relatively simple model now to predict particles. And this is why I like this plot very much. You can see that helium-3 are produced a lot at low energies, then it goes down. But at some point, it meets its counterpart, the anti-helium-3, and they get very close until they basically become the equal production yield at the LHC region. And this is also true for the alpha. So this is alpha particles and anti-alpha particles, and actually we expect them to be produced at the same amount. And the good thing is here, you see this basically penalty factor by adding one of the baryons. This is already visible from that picture. You see it's connected to the large mass. So 1 GeV basically makes a penalty of about factor 300 here. So the chemical potential, the chemical freeze-out temperatures is basically the main player here, and this is connected to the large mass of the particle. So 1 GeV more, 1 GeV more is always suppressing more. And this is then connected to the dependence of the yield onto the e to the minus m over the chemical freeze-out temperature. And the interesting thing to mention here is that the binding energies of all of these objects are rather small compared to this chemical freezer temperature. This is always called the snowballs in hell, where different proposals are made to overgo this. The other model, which I keep very short, is really this old plot from Joe Kapusta here. You have a projectile and a target. They form a fireball, and the fireball emits protons and neutrons. When they are close in phase space, so this a little bit depends on the model. So there are models which can only use the spatial extension, or the spatial distance between these two, and then you expect to form a deuteron. This is the new Eichelin approach, I would say. He used it also before, but the better approach is then to use the full information, so the spatial distance and the momenta should be close to given or below a given value, and I will show some results on this. But the idea is you could in principle form them at any time, but then they could break apart and form again. So at the end, you measure something after kinetic freeze-out. This is here the characteristic temperature, which plays the role in the coalescence model. So the results I will present are done at the LHC, but you know, all of us really know that the big player here is ALICE. So the others are only started soon, measuring also nuclei. And ALICE sits here. So this is the Swiss-French border, which is this stars, I would say. See here the Geneva airport, and it's on the French side. This is Saint-Genis, and there you find point 2 where ALICE is located. And just some details about the measurement, because they will mainly use these two detectors. So this is the time projection chamber and the time of flight detector. They together do a very good job on the particle identification. And I need in addition the ITS, because this can give us the separation between primary and secondary particles, because the world texting is very good in this. ITS, we expect it to be even better with the new ITS, which was installed for the upcoming run 3. So I use these 3 detectors, and you will see some plots in following. And this is, I always say, because we switch from centrality, which is a concept everybody is aware, also to multiplicity estimators, because then we can compare lead, p-lead, and pp at the LHC. And central lead collisions is basically head-on pancakes, and this is more than 2,000 tracks, up to 30,000 tracks in the detector. And the peripheral is just a small overlap, and this leads then to small dn eta, the uncharged eta, and central collision leads to large dn eta, as you will see. So starting with the nuclei, I think most of the things are old for most of the audience. Just starting with the PID, so the particle identification is crucial. ALICE has a very good one, so at a low momenta we can use the time projection chamber, measuring the specific energy loss of the different particles, and we can well separate them over a wide region until they merge. You see here antideutrons and antiprotons merge around 1.2 GeV, and then you need another technique to separate them. And this is usually done by the time of flight detector, where we calculate the mass square or the mass square over Z square. You see it here for deuterons. There's some background which is from fake hits and from mismatches in the time of flight. But you see clearly a signal where we can extract then the spectra from it. From the plot below before, you don't see, actually I go back because it's always hard to see here the blue dots. There are blue dots on the anti-alpha candidates, but you see them clearly highlighted here. And actually this one is this black one I showed you on the initial slide. So really this is one of the anti-alphas measured by using the 2 detectors TPC. You see it's clean here, and the time of flight detector, this is this red inlet here. You see them well separated from the helium-3 candidates. I always mention that star was first, but only some short time. Actually, we saw in 2010 data quite some candidates. We saw 4, and this is the first observation was published in this paper, as you might know. So I always insist here on this interesting plot, because you see nicely that in PP, it's all possible to be explained or fitted by an exponential. So this is a log plot, a straight line, and that plot means exponential law. So this is PP. But when you then start to look at lead and go more central, there's this shoulder developing, which is connected to the radial flow. So you really nicely see collectivity evolving for the deuterons. So this is something I really like on this plot. But there's no hint for radial flow, in particular for that measurement, which was done in 13 TeV. Currently still top energy will go a bit above the upcoming run. But the good thing is when we do our analysis carefully, we check for all the bins you have, for all the centrality intervals you have seen before. We check the anti-deuteron to deuteron ratio, and it's consistent with 1, so see, as it's expected from the thermal and actually also from the coalescence model. I also like that plot. It's rather new from 2019. You see here the pions, kaons, and protons. So this is the standard thing which you do a blast wave fit on and then extract some global parameters. But you see in addition deuterons, antitritons, anti-helium-3, no, it's helium-3 in this case, and anti-alphas. So this is actually the first spectrum of anti-alpha ever, which you see in this plot. And also at the LHC, the first anti-triton spectrum. And you see that this is really nicely described with one global set of parameters. So this is a global blast wave fit, where clearly the small uncertainties of these 3 particles determine the properties, but you can well describe also the deuterons, the tritons, helium-3 and alphas with the same flow field. I think this is very noteworthy. We measured over time also protons, deuterons, helium-3 and alpha, and you see as a function of the baryon number in the nucleon number in the nucleus, you see this is following an exponential law, which is clearly predicted by the thermal model, but actually you can get that out if you do some tricks in the thermal model also. But you also see the same slope on the antiparticle side, which I always highlight. And as I already said, it's about 300, the penalty factor going from or adding 1 baryon to the system. It's basically a suppression of the order of 300. The same is true when you look then at p-lead, but you see the slope is changing. And actually, there's another figure which I did not include, where you also see the protons. It's actually, you go from the 300 to a penalty of 600 to a penalty of 1000 if you go from lead to p-lead to pp. So the slope is changing and the production yield is more suppressed. This is now, when you plot the data I've shown you before, a bit different. You see here, this is from the talk of Reinhard Stock at Quark 2018. I like it because this is the one where you also include the thermal model from Picatinny. Where you see the thermal model actually predicts, or the grand canonical thermal model predicts some constant value here, which actually close to most of the predictions. It's just a higher temperature here in this case. But if you include then the whisk scattering, so you really include UAQMD afterburner, I would say, then you drop down to the value which is also gotten by using deuteron calculation in UAQMD from phase-space coalescence. And here the limiting parameters are the maximum momentum difference and the maximum spatial distance is of the order of 3.5, and the momentum difference is 200 MeV. And this is true for the PP points, which have a low multiplicity, but it's also true for the lead. I always ask Jan Steinheimer to bridge here to see how this evolves, but he's hesitating to do this calculation. So the more prominent plot, or the more often shown plot by the ALICE people, is this one, which has 2 models in it. Has a canonical statistical model prediction calculation here for two correlation volumes, which is the dashed and the full line here. And basically you can say this is kind of the uncertainty of this calculation which we did. And you see the coalescence prediction, which is basically free of parameters. So you really can describe with the coalescence model all data points here, but also with the thermal model, if you do, basically, if you would fit now everything, but as I said, it was a prediction when we wrote this paper, you can really try to describe this in one go. There is also the helium-3 to proton ratio, and you see here now also tritons in, because we take the ratio to protons, so it's not only helium-3 to proton, but also triton to proton. And it's interesting that some points seem to favor here the thermal model, not sure why, and some are on top on the coalescence calculation, but at least people often highlight that there's some tension with these points, but if you take it serious, it's just that one point which has something like 3 sigma deviation. The rest is less than 1 point something sigma distance to the coalescence calculation in that case. There's a new plot of this, looks a bit different because it's focusing only on the small multiplicity region. So this is all pp points and the lead points, which you see here. So for the deuteron to proton, it's really all on top of the coalescence calculation, as you see. But you see here also that the tension, I'm actually not 100% sure that all uncertainties are properly shown here, which you saw before, because they did not change, shouldn't change. You see only at a very low multiplicity you are top on the calculations. These are still in the limit of the thermal calculation, this also, but then these p-lead points and the high multiplicity pp point, they have some tension. So either the model has to be improved, or this is something we have to understand. One can do a fit of these data, and this is then a bit different than the one I showed before, but you see here, this is the 2.76 data, you get the 156, and you well describe also the nuclei in the uncertainties. And the big thing is that you also describe the hypertriton in uncertainties, but you describe it rather well. And the hypertriton, as you know, is a special case. I will come to that in a minute. But one thing I want to mention, because I usually don't talk about that, but it's important when you go to lower square root of S. There's a feed-down contribution for the nuclei. So in principle, the nuclei could be excited, particle excited, and then decay into something with less excitation, so the ground state, and emit particles. And this is interesting in particular for helium-3 and alpha. And you see here, this is something like 5% at the LHC, but it increases to large fraction at lower energies. So this is something I think it's also important to mention. At the LHC, you can say it's nearly not playing a role because our uncertainties are in that range at the moment. We proved that, particularly in the new data sets, hopefully, and for the deuteron and the protons anyway below anything visible here in this plot. Some new measurements is connected to the absorption of the antinuclei, which I think is very important to mention here. This is very new on the archive, but it's a measurement which was performed over years. So long time we used GEAN3, which was patched with a given, connected to a given publication, but then we started to compare also to GEAN4, which does a much better job, as you see here. The interesting thing is that there starts to be some tension if you go to lower momentum. Just to explain that plot, this is the inelastic cross-section of, basically the absorption cross-section of anti-helium-3 in Bahn. This is missing here, but this is the data extracted from different measurements from us, and you see here that they are all in line, and they're starting to, this is the centroid of this point. In uncertainties, it still agrees with GEAN4, but there are some points we still want to bring up, which are here, and they give some tension. So the idea is basically that the rise of the GEAN4 calculation actually is not totally correct. But this is the newest thing. There's also publication of anti-deuteron absorption, which also shows that there's at a very low momenta, there's some difference between what we measure and the GEAN4 calculation. But in any case, GEAN4 does a very good job, and this allowed us then to shrink some uncertainties, which were always in the systematic included. And from that measurement, you can actually now in the next step calculate the anti-helium-3 flux near Earth of this anti-helium-3. And the first question is, how can they be created? The one thing is there could be proton-proton collisions happening in the universe, and this leads to anti-helium-3. Basically, I showed you that we measure anti-helium-3 also in PP. And the other thing would be basically collision of two dark matter particles, which at the end also form an anti-helium-3. And this is what we need to understand. Is it really what the AMS at the end sees here close to Earth? Is it an anti-helium-3 from dark matter annihilation, or is it from a normal background event like a PP scattering in the universe? And there are some calculations which were done in this publication with GALPOP. This is the default transport model which is used in this kind of calculations. And you see here, this is basically before solar modulation on the left side, and you see that the uncertainties are basically, you see here, connected to the inelastic cross-section Alice has measured, and you can see that the uncertainty basically is even smaller when you're in the solar modulation region. And you see this is the current sensitivity of AMS and gaps. So you don't expect, so this I did not explain it properly. So this here is basically the annihilation process which produces anti-helium-3, and that is coming from PP collisions in the universe. So this is where we are at the moment. So the sensitivity has to be increased. Basically, from our point of view, AMS needs much more time to measure these guys.
Benjamin, before you continue, there is a question in the chat on your slide 30, namely the feed down correction for these nuclei. Why these fractions are almost zero for protons, neutrons, and tritons? Well, they are. You can explain, I think. Or do you want to do this at the end?
So in principle, so these excited states always often go also into protons, but the fraction is rather small compared to the protons we anyway have from delta resonances. I think protons are mostly dominated, the protons we see are dominated by deltas, which do this decay. You can now ask about the neutrons. So there's not the branching fraction from feed down is mainly into larger objects if you go to heavier nuclei. So I did not explain it properly here. So there, in that calculation we did in this paper, there we only added nuclei up to A = 5, and from that branching fractions, it's the picture you see here. If you add additional ones, there comes a lot of ambiguity because there are a lot of possible particles if you go to mass 6, and then the branching fractions are also not well known. This one which enter here are rather well known. Or is it generally?
That's only for very low energies.
Yes.
If you go at LHC, this is all essentially immaterial.
Yeah, true. Yeah. Does that answer the question, or should I try to explain it differently?
No, I think it's probably okay, but you wanted to, you posed that question. Is it okay like that? No answer. Okay. So we come back if necessary in the chat at the end.
At the end, yeah, clearly.
Okay, go ahead.
Okay, so the next chapter are hyper-nuclei. And there the interesting thing is, how does this object actually look? Very often it's treated as a deuteron where lambda is bound. This is also what I calculated. You see the mass is of the order of 2.991 GeV, but the lambda separation energy is only 130 keV. This is still the literature value. There's a star update on that. But if you ask the hypernuclei people, they tell you still 130 keV. And if I use this 130 keV to calculate the wave function, I get this red object here. And as a comparison, there's also a triton-like object calculated. So it's also treating a deuteron and a neutron. What you see here, it's not so bad actually from the RMS I get from the triton to what the literature tells you. But if I do the RMS calculation for this large hypertriton thing, I get RMS radius of 10.6 Fermi. And as Peter always says, this is the ultimate halo nucleus because it's larger than even a lead nucleus. And this particle is unstable, it decays weakly. So in this case here, anti-hypertriton decays into helium-3 and pi plus. This is the most famous channel and the one we published most of the things. We are also working as started on this three-body channel, but there we usually have problems with the Monte Carlo. This is a tricky thing. But also here, STAR was first. They basically observed it in their first runs and published a nice science paper, which is also worth to mention. So this looks old because 2016 is so old, but this is still a very good plot, I think, because you see we really have a clear signal. If you look at the first publication of Alice, there's even in one of the two shown pictures, you see just one higher data point over a background, but this is really showing you we are getting much closer to what we want. We need clear signal and want to make precision measurements here. On the right, you see then from that data set, the PT spectrum in 10 to 40% centrality. And you see here a blast wave, which is not coming, so the parameters of this blast wave are coming from pi and k and proton, basically what I said before in the global fit. And you see it's nicely matching the data points. So also from that picture, you can say that there is radial flow. Also in the Hypertriton, this huge object, there's still flow visible. And the other thing to mention is also here the anti-Hypertriton to Hypertriton ratio is unity. So we really have equal amounts of Hypertriton and anti-Hypertriton. This is a very nice plot from Anton, where you see that the light particles are all matching to the thermal model calculation. This is a grand canonical model to 2.76 TeV. And it also describes the gypsy yield. And this is important to just explain it quickly. The charm quarks are basically produced in the hard scattering at the initial collisions. And this is connected then to chemical equilibrium. So the charm quarks, which are produced initially, so we need to know the charm cross-section, are then populating states like the others are allowed to. And you see the gypsy is in this model well described. So the only input parameter which is extra is the cross-section, and this cross-section is actually coming from PP and not from that lead. And you see this is basically a jump of a factor 900, which is connected to this cross-section or to the gamma C, so that basically to the fugacity. And if you use that factor then to compare the spectra of Hypertriton to the spectra of the gypsy, which is shown here. So the gypsy spectra are the red points, and the Hypertriton, this is a different, this is the 0.76, if you wonder why there are 3 points and not 4. So this is centrality of 0 to 10%, this is centrality of 0 to 10%. You see the data points nicely overlap, and you see here a calculation from Peter, Anton. Actually, I think the player was Marcus Köhler, who did that. It's a statistical harmonization model where you on top add a hydro, and this is really nicely describing the gypsy and the Hypertriton at the same time. So this is really very nice plot where you see that the nature of these particles are completely different. The gypsy is about 600 MeV bound, and the Hypertriton is only 2.35 MeV bound. Remember the lambda separation energy. It's a deuteron, and the lambda separation energy is only 130 keV. We continued measurements, so these are the most recent experimental results which you see here. So we measure the Hypertriton also in PP, and you see the good thing, a nice peak on a smaller background. Clear, less particles are produced. That's why it also sits at a lower value here. But this is Hypertriton over lambda ratio, and you see at about 30, you see the point for the p-lead. So this is what you can find here under this archive link, and the PP is still preliminary. You see they have some tension, but they if you take the uncertainty serious, it's fine. So they are in agreement. but they somehow point here more to the two-body coalescence calculations in this ratio. If you look now to the prominent S3 ratio, which is the double ratio of hypertriton to helium-3 over lambda to proton ratio, you see that there's a large difference between the thermal model calculations, basically the same as I showed before, and the coalescence calculations. And here it looks, so this is still in agreement with the thermal model and this basically in the middle between thermal model and coalescence model, but the PP having small uncertainty lifts its head on the coalescence. But we still need to do better measurements, and we are actually working at the moment on a trigger data set to extract the kind of measurement here. So another PP point at a lower value of multiplicity. But this is still something which we want to populate, as you saw for the deuteron and the helium-3 in the upcoming run. The other important thing which is usually discussed, I didn't want to skip that, is the so-called Hypertriton puzzle or Hypertriton lifetime puzzle, which was connected mainly to these four measurements here. They are star, Hi-Fi, and Alice. They were lining up, but they were quite some, actually it's 1 sigma or so away from the lambda lifetime. But then star had another point in this publication here, and then it was quite some more sigmas of, this was 2.2 or so when we did the world average. But there are new measurements which you see here now, and now also star is in agreement both with the PDG value for the free lifetime and the world average which you see here. There's actually something which I would like to point out. So this grayish thing which has large uncertainty here because they did several calculations. This is the center value when you take the 130 keV binding energy of the lambda, is rather better fitting to this old, or the first measurements we did. There's no real tension towards the new points, but it's interesting. So the idea behind, I did not mention, I think most of you know, is that the hypertriton is this deuteron lambda bound state, so they're well separated, so the lambda is basically decaying freely. This is why you expect this free lambda lifetime or something very close to the lambda lifetime, as you see here by different model calculations. So it's not solved, but it's interesting that the world average moved up because the uncertainties shrunk for star and for Alice. There's a new measurement from Alice to determine this lambda separation energy. You see here the scattering around the center value, and the center value gives you something like a separation energy of 55 plus minus 62 keV. And if you compare this to the other measurements, so this is star and this is Alice here, there's no real tension, but it's interesting that all these values come basically out. You see here an old value is actually a negative, so it would not be bound by the resonance. Okay, how do I do time-wise? I did not check.
You have still have 20 minutes.
Okay, then I will go also to this rather old stuff, which ends with something new. So this is the Hi-Fi measurement on the deuteron plus pi minus invariant mass and the triton plus pi minus. And as I already explained in the beginning, this is the only collaboration who saw that. Is this open circles are a mixed event background, and on top you have the data, and they claim here this nice peak. Actually, they don't claim it anymore, but in their first, when they first discussed this, this was treated as the lambda n bound state, and they also see something, as I said, in the triton plus pi minus channel, also over the mixed event background, and this was then discussed as a lambda n bound state. Unfortunately, there's no real result I am allowed to show you on the lambda n bound state, but I can tell you that we don't see it. This is actually the current status. I know that there is a particular experiment at JLab which used the tritium target to also test if they see this, and the results I saw so far also don't see it. So we didn't see that. And the H baryon is a long story, as most of you might know. So it's a hexaquartz state, which was predicted in a back model calculation in 1977 by Jeffy. It can, depending on your point of view, treat it as a 6-quark state, as I said, or as a bound lambda particle. The quantum numbers are the same, and some calculations actually give the same decay modes for that object. This was studied, it's not so recent anymore, in 2011 on the lattice by 2 collaborations, and they both found bound state, depending on the calculation that you see here. So the HAL+CD did several points. The NPL+CD collaboration did at that time only 1 point. And the issue is that you still have to propagate it to the physical point by a chiral extrapolation. And if the chiral extrapolation is done, it's unbound, the H baryon, by 13 plus minus 14 MeV. So it's somewhere in the middle between lambda and Xi proton threshold. Or in the Heidenbauer-Meissner, it's very close to the Xi proton threshold. So we would expect a resonance state from these discussion here. So this renewed the interest in experimental searches. So we also looked for that. But there's a new lattice QCD calculation, which even says they had done a proper chiral extrapolation, which again says it's bound. This is very funny, and this is from December last year. So I wondered that there was no real discussion among the hyper-nuclei physicists so far. At least I did not realize that. This is how the invariant mass looks like. So we looked at anti-deuteron pi plus because this is cleaner for us. And you would expect this large peak here. There's no large peak, so we set an upper limit. And the same is true for the H baryons and lambda proton pion. You would expect a bound state here or a resonance somewhere on the way. You see there's also no resonance. So either it should be very wide, that it's hidden among these counts, or I don't know. But what we did, we treated it both as weak decays and calculated for this region here upper limits. And this is done here as a function of the decay lengths. You see for the anti-lambda neutron bound state, there are huge factors off, even if you expect it to live up to 3 meters. This changes a bit for the H baryon. If you go to large decay lengths, at some point you need to get the 4 final state particles from that thing inside the TPC still, and this makes then this value very close. The upper limit is very close to the Eternal model prediction, but this is actually the region where it's supposed to be if you ask the theorists. This is this close to the decay length of the free lambda. And I think I switched it off. Yeah, okay. So in principle, I have also another parameter space which I removed. But if you do then the calculation at the branching ratio of 55 and 64, so this is basically lambda branching fraction, and this is the fraction we got. So base calculations are from Schaffner-Bielich. To get this branching ratios, you see that all of these particles, proton, lambda, Xi, even anti-alpha is well described by the term model, but these upper limits are more than factor 25 to the terminal model. So we really think these guys are not produced. The newer measurements, this is what I said initially, is connected to the correlations. So what we do in ALICE, you know, there's a whole industry, I could say, to measure now correlations and extract the interaction. And this is done when you at the same time fit proton-proton correlation. It's the correlation function as a function of K star, which is the relative momentum in the, it's the half relative momentum in the center of mass of the 2 particles you measure. And you see here the protons are perfectly, so proton-proton correlations are perfectly fit by Coulomb and argon. So we definitely know the interaction, yeah, which is basically, you see here the correlation is in experimental definition the same sign compared to mixed event. And this is theoretically described as an integral over the source and the squared wave function, which is basically what we want to see, because the source function is what is extracted from this measurement here of the protons, where we actually know the interaction. So in other measurements, which can be compared to this one, fit at the same time, you can extract the interaction. This is then shown here for the lambda lambda. It's basically also the correlation function as a function of k star. See a femtoscopic fit, and this is then used in the next step to extract basically the phase space of scattering lengths and scattering lengths in effective range d0. So it's d0 and the inverse scattering length, which is shown here. So a bound H-type baryon would be basically negative inverse scattering length. So this white region is the only leftover for a bound state of the H-type baryon. And we are trying in the next run to get this also closed with the data. And you still have a large freedom for the H-type baryon to be a resonance state. You see here, this lattice is basically the one I mentioned before when I introduced the H-type baryon. So the Hall QCD calculation basically expects a resonance state. This brings me to the outlook and the summary. So this is an old plot. They are newer, but I'm not allowed to show them. So the run 2 is over. I showed you results from run 2, but we are about to start run 3. We had a pilot run, which was very successful, where we only had injection energy. So this was 900 GeV. But run 3 and run 4 will come. They start soon, and we will take data with 50 kilohertz net interaction rate. And this is possible because we updated basically all detectors, but 2 very important ones. So the TPC was changing from multi-wire proportional chambers to gems and performing well. And the ITS was changed to complete setup of pixels. Before we had mixed technologies also to allow for PID. We saw then it's not necessary to have PID for the very low momenta. But what I showed you was basically results on A equal 2 and 3 particles, and we think that we can go now to A equals 3 precision measurements and start really to go to A equal 4. And this is shown here. You see here hyperhydrogen 4 and hyperhelium 4 predictions. So this is the expected yield, which you should see here. But the more important thing is the significance, and you see this is really above the 5 sigma level, what we expect to measure for these particles in run 3 and 4. This brings me to conclusion. So I showed you Alice has measured quite a lot of exotic objects, nuclei, hypernuclei, hyperhydrogen, and set upper limits on exotica. The particles that are produced that I discussed are all loosely bound objects, and still they are well described by the thermal model. But the Coalescence does also a good job. And in fact, you see here the same plot I showed you before. It looks a bit different because it's full point. It's only the markers are changed a bit, but you see also star points on top. So the magenta are the Alice, they are well described by the thermal model. But you see also the star deuterons, which I put here in this small review. In addition, is also well described by the thermal model. But clearly, as I try to point out, there's new and more precise data to be expected in the next years, also from the LHC, not only from the beam energy scale. Thank you for your attention.
Well, thank you. Thank you very much, Benjamin, for this exciting review of all what is going on. Actually, it's even a subset of what is going on, but a lot of what's going on in this area of research. There are something like 5 or so questions in the chat. And of course, I ask for more questions from people who just should raise their hands. I don't see any in the raised hands yet. So maybe we start with what was discussed in the chat, and meanwhile people can raise their hands for more questions. So in the chat, the first question registered is by Uli Heinz, in which he asked, do PP and P-LED collisions have the same multiplicity? Why this is with respect to slide 43, 44?
This is high multiplicity trigger in PP, and
Yeah.
it's funny that it's actually nearly the same multiplicity. It's just by chance. So
It is selected to be the same multiplicity.
It's not. It was not on purpose actually. So for the p-let, we only picked 0 to 40% for the measurement because there sits the most of the yield. So it's basically central p-let where you see a good signal of the Hypertriton, and the PP high multiplicity trigger is just coming out to have nearly the same multiplicity. This was not on purpose, but it comes out like that.
It looks like it has enough statistics that you might be able to split it in multiplicity in order to check the tendency with which is predicted by the models.
I think Michael, who did this analysis, is listening. He's not a fan of splitting it further. But as I said, we are about to somewhere here.
Run 3 will do it all, yeah, okay.
Yeah, also that, but we have still from run 2 trigger data set where we end up somewhere in this region.
Okay.
And in run 3, there is no triggering anymore. We'll measure
Exactly, continuous readout, we take everything.
Yeah. Okay, next question in the chat from Jan Steinheimer is the lambda yield corrected for the sigma 0 contribution in data and in coalescence?
No, it's not.
Hi, Benjamin. So what does that mean? So the lambda includes the sigma 0 or? Okay.
So the problem is we have a first measurement which should be published on the lambda 0. So we could basically try to extract it, but only in PP. And there's a definition. So electromagnetic and resonances are treated in ALICE as primary particles. That's why it's basically lambda plus sigma 0.
Okay, thanks.
Okay, next question in the chat is, this is a comment by Joachim Stroth that Hi-Fi will have another run at GSI in March this year. This is next month.
Yeah.
So we look forward to seeing what is coming from there. Okay.
It should have a better resolution. So if I can add some.
Yes, please do.
The hope, or it's designed with this Vasa fragment separator measurement, that the resolution of the peak gets much narrower because it was also very wide. For us, this is nearly a resonance what they measure. It's so wide, this particle. The weak decay should be small, but in the measurement of Hi-Fi, which has a special design, it was very wide, the object which comes out.
Okay, I think that is essentially all that is in the chat.
Okay, so question by Nu, I think.
Well, now there is a raised hand by Nu, and we go through the raised hand. So Nu, please.
Yes, thank you, Benjamin, for a nice talk. I have few questions, but I think the same thing. So I think it's page 22. You showed the plus 12 fit. My question to you is, have you tried to fit, for example, proton and the deuteron individually? Do you see the same result, let's say, parameters like a beta and a T? We actually found, now it's also, in the 3 GeV collisions, we found that they are different. We just noticed that they are quite different. Then we went back to 200 GeV, also different. It's interesting enough, if you fit them separately, it looks like a deuteron freeze-out parameter temperature-wise is higher, and beta is a little bit smaller.
So you say,
and it's a little bit counter-intuition, but my guess is because if we taking just the coalescence approach, it's because the deuteron sample protons and neutrons from freeze-out distributions. Maybe they're in favor of the higher momentum region, or more straight distribution, let's say. So yeah, that is.
Maybe the question is really your question is what is going on at the LHC? Can you answer that question, Benjamin? Is there any?
the answer, the direct answer is, so if we do fit of the protons only, you get totally different parameters compared to the deuteron. What I did not do, this is actually a good idea, to leave out pions because they have the smallest uncertainty, to leave out pions and kaons and try to fit basically green and red together. This I did not do, but this is a good idea to do. But the value which comes out from that fit is rather, then it makes sense compared to the fit of only pions, kaons, protons.
Because
you have to specify the fit range, and that makes things more complex.
Yeah, but if I follow the suggestion of Anu, I don't have to restrict it too much. So the point is, protons I might restrict, but you see the others are fitting over the whole region. So usually it's the pions where when you do such a kind of, which have the most restricted region, because it's called the resonance decay, so it's very low.
Right. If we just take coalescence picture, I'm not sure it's 100% correct. You can do PT divided by the A, then you select a similar region. That is coalescence picture.
Yeah, that's a good idea to do it like that.
Yeah.
And leaving out some things.
Correct. Yeah. So now I think another plot, a similar plot, you compare Hypertriton and J5 on the page 40 or something. So in this, you claim they are similar. Are you saying they are I mean, my question is the same I asked Peter before, I believe. Are they coming from 9 quarks or 2 quarks? Or what is going on behind this physics-wise? So, and of course, there's lots of room for imagination because statistics is not very good.
Absolutely. No, this is when I showed this to Uli. Uli said, "You take more data, and you will see the uncertainty shrink, and you will see that one will be dead and one will be dead, so they will be separated." But
Uli is right. Yeah, yes.
But from that, it's definitely, you see, it's connected to the mass. So the flow is connected to the mass, which you see, and this is basically roughly the same. So it's 2.9 to 2.89 for the two. The mass difference is so small that they basically have the same flow. This would be my direct interpretation.
If it's a mass, so still coalescence or not?
Yes, you get in the coalescence model, you just get the sum of the momenta, which means if you have the same flow, it's the sum of the masses.
Well, I'm not convinced because my first question, because when you do coalescence, you still have to sample this.
But you don't need coalescence in order to, I mean, just hydro.
Yes, it's not coalescence. Yes, but this plot, look, this plot is there to make sure that these comparisons will be done with high quality. I think it is still amazing that the spectra seem to agree on that level of accuracy, but I will agree that we should not speculate much more because we will have a factor of 50 more data in maybe 2 years from now. And this question will then be, as always, precision leads to trouble. And we will see where the trouble will be on which side.
Okay. If I may, I have a last question.
Sure, go ahead.
And you did not show, Benjamin. I also do not remember precisely. There's a prediction of thermal prediction and coalescent prediction of, I think it's a Hypertriton. Xiaofeng may help me. A star result and Alice result are different dramatically. Alice result is very much higher with bigger error bar. Star result with low energy, we have energy dependence, it's much lower. Do we understand? This is already for 2 years. I have
you mean the 3 GeV data? Or what?
No, we have energy dependence. Xiaofeng, do you know what I'm talking about?
I think it's the double ratio, the triton times proton divided by deuteron square. So that is the data point.
That's right. Yes, our data, at the lower energy data is much lower. Even 200 GeV consistently lower, yes.
Yeah.
Do we understand?
Yeah.
That's right. This is the plot. Yeah.
We-
This is the right.
I know this plot since 6 years, and we have no explanation. It certainly is inconsistent with the Alice result.
Mhm. Okay.
There's some tension between the 200 GeV since
Yes.
the beginning, actually, since the science paper, there's this tension.
But the B-managed scan data is still consistent with 200 GeV data.
Yeah.
That's why.
No, but I think this is also a weakness of something which actually I think is a weakness of the coalescence model, that one has to resort to such ratios, which I think is terrible, because I'm not convinced, for example, that the lambda and the proton are correct. You construct ratios of particles which are not part of the thermal description, because if you don't correct for the S matrix correction, the protons will be off. So this is a very complex business to use such ratios, and it's very unfortunate that we have to do this in this coalescence description. The yield by itself, the yield of Hypertriton and helium-3 and lambda and proton, all these yields should be simultaneously described, and not just these ratios. And the ratios hide things more than they explain.
Yep, the plot I mentioned is a triton times proton yield divided by deuteron squared.
Yes.
Not involve a strange hadron.
Yeah, but that's still the same. You need to understand then the tritons and the protons and the deuterons, and the tritons are much more difficult to measure than anything else.
That's right. Okay, thank you.
Anybody else? Any other questions?
Kaija has announced another question in the chat.
Okay.
Yeah, hi Benjamin. Last talk, I have difficulty to raise hand. I don't know why. So yeah, this so a follow up for the triton or helium-3 production. Could you go to page 27? Yeah, here. So I see some data points agree with the coalescence prediction, and some agree with the statistical hadronization model. And so basically, I think for the B-managed scan, it agrees with the coalescence calculation, which has done by myself and also by Wenbing Zhao. And so that's the reason why B-managed scans see a very low double ratio of triton times proton divided by deuteron square. And so here at the LHC, it seems difficult to distinguish, because some data points are higher, like by almost a factor of 2. So I don't know. So is it possible, when you increase the statistics, one can distinguish between these two predictions?
Yes. So this is exactly what I try to say. In the end, we hope to improve the statistics on all of these guys. So this is already, when you see here the red points.
Yes.
0.76, you see already going to basically run 1 to run 2. We already shrink the uncertainties, but it looks like then it goes there. This is statistics. We need precision here to test this really. But still, the models are very close. This is the problem. This is why for us, we always say that the real test is the Hypertriton, because there you see the difference. In particular in that region, in that quantity in the S3, you see really the thermal model has a completely different trend as the coalescent model.
But Benjamin, then I think you should, this S3 is the trouble. Then I want to see an agreement for all of these particles and not on this ratio. Yeah, which of the particles is off now? Is it the Hypertriton or the helium-3 or the lambda or the proton?
you see that it's the points already look different here. So it's
but this is still at but this again a ratio to lambda. You don't know whether the lambda is the or the hypertriton.
So
it should not be too hard to satisfy Peter, I think.
Huh?
It shouldn't be too hard to satisfy people by taking the ingredients and plot them as predicted.
I was asking that since, as Benjamin knows very well, since many years, but I don't get it.
So these are models which were predictions actually. So Kair did the calculation before we had these points, and Volodya did the calculation before we had points.
So Peter, it's indeed not quite true. If you take Volodya's calculation, who did the canonical model as a function of multiplicity for protons and lambdas, you actually do know that the canonical with a small volume does not describe neither the protons nor the lambdas.
Yes, right.
So that's why also what Benjamin, when you on slide 22 say that both coalescence and thermal model describe, no, maybe it's not this one, the one where you had both the thermal model and the coalescence model. This one, yes, go back. Yeah, here, where you say the both describe the data well, that's true, but here again, only for the ratio. And there, Peter's point is correct, because the canonical model with a small volume, the black curve, fails rather dramatically in the protons, as we know, because protons are constant and it breaks. So indeed, Peter is right, but it goes sometimes one way, sometimes the other way.
Yes, and I think we have to do this analysis also consistently. And there is this question, as you all know, that the proton yield is not easy to describe unless as we believe you have to use this S matrix correction, and this is not done in any of these calculations.
Yeah.
Okay, I don't see any other. Yes,
I don't know.
Yeah, if I may, if there's still time, can you go back to the slide where you showed the S3? So that was as function of beam energy. No, okay.
Multiplicity.
I wasn't sure if this was a function of beam energy or as function of multiplicity, but yeah. Okay, thank you. I thought I looked wrongly as I was, but if I say to Peter one more thing, like if you do coalescence, of course, a lot depends on what your underlying model is in which you use to describe the protons and lambda, as you said. So of course you better try your best to get this right. And that's basically what we're trying to do. And then if you do this, of course, there is no such thing as one coalescence result, because different underlying models give different coalescence results. So saying coalescence says this because one person did a coalescence calculation, and then comparing thermal models as this is a little bit, So
and that is the same as I claim that is similar to trying to force it into ratios like S2 or S3, which have many ingredients.
They do, but they have the advantage that you don't have to look at 12 orders of magnitude, where you also sometimes don't see it.
But in the end, you don't know where the discrepancy is.
Right, that's something you have to really figure out. Not only look at one ratio, but also look at other things and try to get the yield right and so on.
Yeah, very good. Any further questions?
Sure.
Yes. Could you go to the slide 26? I think still the production mechanism of this light nuclei is not quite clear for us, whether those formed from the coalescence or thermal production. You see that from the thermal side, that at the low multiplicity, this suppression at the low multiplicity is due to this canonical suppression. From the thermal model, from the coalescence model, the suppression is mainly coming from the size effect.
Exactly.
That's right. Yeah. So, I mean, still, I think the thermal model and the coalescence, we need to kind of distinguish it. And you already see large difference at this S3 value, right? Prediction from thermal model and coalescence. So it's kind of different. But for the light nuclei, individually, their yield and also whether, I mean, the production of this light nuclei, of those light nuclei, still not clear for us. So do you agree this?
Absolutely. This is why we look for different quantities, but yeah, at some point we have to end up where Peter wants to go, so really compare yields with models.
Yes, so looks like the double ratios, for example, the S3 has more distinguished power than
Exactly.
this single ratio.
I don't know. I disagree on that statement, but
Yeah.
I think that you can never do better than looking at all the individual weights, individual yields separately.
Other than Peter, of course, that coalescence per definition only
Yeah, I know that's
makes
part
ratios.
of the problem. That's part of the problem.
That's part of the model. Yeah.
Yeah.
That's not true.
Well. Okay. I
Yeah,
think there will be lots. Let me maybe make a few comments here. There will be lots more data coming exactly on these issues as we start now run 3 at the LHC. We will in particular have precise data on all of these nuclei as a function of multiplicity, where there is very little room to maneuver. And I'm sure in 2 years from now, we will still have a beam energy scan seminar where these results will be discussed now, then from low energy all the way up to LHC. And I trust that as we have more and more data, that the truth will float to the top. So anybody else? Any other questions? No, I don't see any more. So I think.
May I ask another question? So in the like small collision system, like PP collisions, why could you, like in statistical hydrogenization model, you treat basically like the deuteron as basically as point particles, but in coalescence we treat the deuteron using their sizes, using different sizes for deuteron, triton, and hypertriton, which I think is more reasonable. Why can you treat, why the size? I think the size should be taken into account for PP collisions at least, because this collision source is so small compared to the size of deuteron and hypertriton. Could you give some comments?
In principle, the thermal model doesn't care about the size. If you put a size, you get a different volume, but it's not really changing the fit. It's just coming out of how you treat the particles in there. But the interesting thing is when you use the S matrix, actually the S matrix is kind of giving all particles a kind of size because it's connected to the scattering phase. And this is something where I'm also trying to get some nice result out for the deuterons, because then in practice, basically you do a correction on the size in some way with the phase, with the scattering phase. Yeah. But in the thermal model which is used here, this suppression really only comes from the canonical effect.
Yeah, I mean,
particles, yeah.
I mean, physically, the finite size of these loosely bound clusters cannot be simply neglected in particularly in small system. Either you use any models. That's the size, the finite size should be taken into account. And the coalescence model just describe this very literally, I would say. So yeah, thank you.
But I think if I put a size for the deuterons, it actually, the only thing is changing is that the temperature is slightly changing, and but the description will be basically close to what we have now. So this was in principle tried also by Volodya. You have these papers where you put the twice the proton size to the deuteron and so on, and you still get a reasonable fit, reasonable description with the thermal model. So you are totally right. In principle, it would make sense to put it in, but it's interesting that it works without.
Thank you. Thank you.
Okay. I think it's 15 minutes past 4 European time, so we have run for an hour and 15 minutes. I think it's time to thank Benjamin for a very nice and concise and at times provocative seminar. And with that, I think I will close the meeting today.
Okay.
Thank you.
Thank you.
Thank you, Benjamin.
Thank you.
Thank you, Peter.
Benjamin, for this very
Yeah.
nice.
Bye.
So bye-bye, everybody.
Bye-bye.
Bye.
See you next time.
See you next time.